the title is Mirror Symmetry and Cluster Varieties. And the subtitle here is What's the Deal with Cluster Varieties? So, right, I intend this to be sort of an example-focused talk. I mean, maybe if I have time in the end of the talk, I'll sort of explain my personal some of my research on cluster varieties, which is a joint with Ian Lay, as I promised in the abstract. I think that most of the talk will just be sort of focused on explaining explaining some basic ideas in the theory of cluster varieties and some basic features and how they behave under mirror symmetry. So yeah, I'll be focusing on examples. So hopefully I want the whole talk to be like comprehensible all the way through. So I definitely want people to stop and ask me questions if there's anything that seems confusing or that I've rushed through. I mean, I'll be going through, this is a mirror symmetry talk, so I'll be spending time on both the symplectic and algebraic sides. So hopefully I can do that in a way that's comprehensible to people who prefer one side or the other. Okay, so whatever a cluster variety is, I'll tell you what my favorite cluster variety is. My favorite example of a cluster variety is C2 minus XY equals 1, which another way to say that is P2 minus the union of a smooth quadric and a line. Okay, so what are some features of this thing? Actually, I take it back. I'm going to change the names of my variables. So in cluster theory, these variables often go by the names A and A prime because they're mutations of one another. Oh no, sorry, I'm still getting used to writing with this fancy new tablet computer I have. 2-in-1 computer, whatever it is. A prime is equal to 1. I'm going to set B, the variable B, I'm going to set to A prime minus 1. So B is something, this is a variable that is always non-zero. And it doesn't mutate at all in the cluster algebra. So this is an example of what's called a frozen variable. Maybe it'll become more clear what that means. And if not, it's okay. I just want to introduce that notation, that little nomenclature, so in case people see that again later. So we want to study, let me give this variety a name too. Let me call this variety X. We want to study this variety by, whoops, sorry. We want to study this variety by, so study X, using the map that takes it to this variable B. So I have a map from X to C star. That's the C star where the B variable is living. And if I think about what this looks like, so okay, so that's my 0 in C star. Now, if B equals A prime minus 1 is anything other than minus 1, so at a general point of this map, my fiber is going to be a copy of C star. And then I can see if B is equal to minus 1, then my fiber is going to be, it's going to develop a node. Okay, so that's the, that's what this map looks like. And then this is helpful. So now the thing which I would like you to observe, all right, I'm going to go to a new page now, but I'm going to redraw that picture. I'll probably just keep redrawing this picture the whole talk since it's such a fundamental picture for me. General fiber C star, special fiber something nodal. The thing to notice now, so this is the B plane, is that you should observe that if I take X and delete the locus where A equals 0, then this thing is a copy of C star squared. Right, so the A equals 0 locus, maybe I should have written that in another color. Let me underline it in yellow here. This is the A equals 0 locus here. right? Because this point here, this point here in the base was the point where AA prime is equal to 0. That's what this fiber is. AA prime is equal to 0. So that's what these two components of that fiber are. They're the component where A is equal to 0 and the component where A prime is equal to 0. And I can see that if I delete this whole component, in particular, what I'm deleting is I'm deleting this singular point here. I'm deleting this whole thing down here. So what I end up with is just a copy of C star squared, which I can treat as having variables A and B, right? So the B variable is in the base and the A variable is in the fiber. It's also true that I could have deleted the other branch here of this singular fiber, x minus A prime equals 0. And that's also going to be a copy of C star squared, right? Where now I've forced my A prime variable to be 0. So a cluster variety has these two torus charts. So I have these two torus charts. And on the overlap, they're related by the equation A prime is equal to B minus 1, or B plus 1. Sorry, B was, go back a slide. B was equal to A prime minus 1. So A prime is equal to, sorry, I'm going to go back. A prime is equal to B plus 1. Right, in cluster theory, the positivity is very important. It's important this is a plus 1 for some reason. I'm telling you sort of all the things I've learned about cluster theory from talking to actual cluster theorists. So I'm not an expert at sort of the combinatorics of cluster theory, but I'm picking up things slowly. And so this is sort of this is what cluster theory is all about. So this example contains like the fundamental thing of cluster theory. The fundamental feature is these torus charts that are related by coordinate transformations like this. Okay, so that's what a cluster transformation is. It's that coordinate transformation on those torus charts. And then there's one other feature which I would like you to note. Also observe that X has a toric degeneration. So I'll call this script X over CT. And I'll call this script X. This is going to be C3 in variables A prime T minus A prime is equal to T, right? So I can see that for T not equal to 0, XT is just equal to my X from before, up to a rescaling of my coordinates, right? At T equals 1, it's literally the same thing. When T equals 0, XT is just equal to a copy of C star squared. Right, because it's equal to, C2 minus A prime is equal to 0. One thing that we are going to see later in this talk is that these two, and let me kind of draw a picture maybe of what's happening in this B plane. Here's my C star B. What's happening is that this T coordinate is telling me that this singularity is shooting down to 0. Sorry, that's a little arrow. He's running down to 0. So in the T equals 0, the singularity has disappeared into here in this B plane. Sorry, C star B. Cool. So what we're going to see later in this talk, I'm going to a new slide here. We will see, maybe, I don't know if we'll actually see it in this talk, but what we'll see is that these two features are swapped by mirror symmetry. These two features, which are toric charts and toric degenerations. Oops, okay, I ran off the edge, but you can read what it says. Toric charts and toric degenerations are exchanged by mirror symmetry. Cool. Any questions so far? Okay, so let's explain now, I'm going to go now to the algebraic picture of what a cluster variety is. So the official sort of algebraic definition of what a cluster variety is due to Gross-Hacking-Keel, later expanded on in work with Kontsevich. So okay, Gross-Hacking-Keel. And what we learned from them is that cluster varieties are a certain class of log Calabi-Yau varieties. So a log Calabi-Yau variety you can think of as you start with a compact variety, and then you have a holomorphic volume form with log poles along a divisor, and then you delete that divisor. Right, so an example of that, sorry, I'm just saying this out loud, an example of that would be a toric variety. You know, any toric variety has a, maybe I'll just give an example. C star to the n inside of toric variety has holomorphic volume, holomorphic top form, yeah, volume form, whatever, volume form, you know, dx1 over x1, wedge dot 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 wedge dxn over xn. And this is something that has a log pole along the toric boundary divisor. So this C star to the n is the simplest cluster variety. So this is the simplest cluster variety. Right, so maybe if I said that the last one was the simplest cluster variety, I was sort of lying. I guess the simpler thing is C star to the n is the simplest one, but that one is less interesting from our perspective. I mean, nothing is happening there. So the first interesting cluster variety is the one we discussed before. So how do we get more general cluster varieties? So GHK explained to us that cluster varieties are obtained from toric varieties by non-toric blowups inside the toric boundary divisor. So let me explain what that means now. I'm going to go to a new slide. It's too bad you can't have two of these slides open at once or something. I have a whole bunch of feature requests for the Blackboard and Zoom people, but it seems difficult to submit them. They're overwhelmed at the moment, but I don't know. Right, so what do I, oh yeah, so I was going to explain, yeah, what this non-toric blow-up situation was. So let T be a toric variety. So let me do this in detail now. So let T be a toric variety. Toric variety, whatever. And let's assume that T has no, let's delete, so let's delete all the boundary, all the parts of the toric boundary that are of codimension 2 or greater. So delete the codimension greater than or equal to 2 boundary. So in other words, in terms of the fan, T has a fan with only one-dimensional cones. So an example of what I mean is start with T equals to P2, and then delete the points, you know, 0, 0, 1, 0, 1, 0, 1, 0, 0, since those are the 3 points in the that are codimension 2 inside the toric boundary. Sorry, I should have said codimension gradient toric boundary strata. I mean, the boundary comes with a natural stratification by components. I don't know. Okay, so that's my starting point here for the construction I'm about to say. So now pick pick a boundary component, D, and since I deleted all the codimension at least 2 parts of the boundary, those were all the parts where the different boundary components were touching each other. So D, before I deleted that, D was itself a toric variety, right? The components of the boundary of a toric variety are themselves toric varieties, but I just deleted the boundary of D, which means that D is now just a copy of C star to the n-1. What I'm going to do is I'm going to take a linear subspace in that C star to the n-1. So take Z is equal to, let's just say x equals 1 inside this C star to the n-1 inside of D, and blow it up. So we now have our original toric variety T, and then we've blown it up in this variety in this codimension 2 subspace Z. This is the sort of non-toric blowup that I'm talking about. So this is the GHK non-toric blowup. And then the cluster variety is, once you do that non-toric blowup, is blowup ZT. So once I do that non-toric blowup, then I delete the proper transform of the remainder of the toric boundary. So their definition, so the GHK definition, is that a toric variety is a log-Calabi-Yau variety, which is related to a toric variety by a sequence of which is obtained from a toric variety. Maybe I'll say that.
You mean cluster variety?
Sorry?
You mean cluster variety?
Oh, sorry. Yeah, thank you. I meant to say cluster variety. I got confused there. A cluster, so a cluster variety in general is a log-Calabi-Yau variety, which is obtained from a toric variety by a composition of these blowups followed by removing the proper transform of the toric boundary divisor. So that's the definition of a cluster variety for them. So I'm about to do an example. So before I do the example, let me just make a remark that this is actually different than the definition of a cluster variety, which cluster theorists care about, in the sense that maybe I should write this down because it's something that becomes important. It's something that could potentially become important to you at some point. Let me just put it this way. This object may differ in codimension 2 from a traditional cluster variety. So, okay, I haven't said what a traditional cluster variety is, but there's sort of an original definition, which is like you have some combinatorics, and that gives you a bunch of toric charts that are related by some combinatorial data, and your cluster variety is the union of all those toric charts. When you look at that union of toric charts, you find that it looks very similar to the variety which was just constructed using the GHK thing, but it might be that you're missing some codimension 2 stuff. Of course, if your variety was affine, then maybe you shouldn't worry about that. I mean, you know, if you know an affine variety up to codimension 2, you know everything. I just want to put that as a remark. Oh yeah, and I should add another remark here, which is actually much more important, which is that the toric chart on a cluster variety is the image of the torus. So inside the toric variety T, T was my toric variety. It has a dense open torus inside it, which is C star to the n. And I have a birational map from my cluster variety to my toric variety, right? Because what I did was I blew up my my cluster variety, and then I deleted this this thing here. So I have a birational map to the C star to the n inside that toric variety, if I put it that way. And so the toric chart in the cluster variety is the image of this torus inside the toric variety under the birational map relating it to the cluster variety. Whoa. Okay, so that's where that structure on a cluster variety comes from. Now I'm going to do an example, which is my favorite example. Maybe I'll move to a new page so I have a fresh sheet here. So my example is, so I'm going to take my toric variety to be D to be 0 times R. I haven't lost connection, have I? I just got a warning that my internet connection is unstable. No, people can still hear me. Okay, good.
Barely.
Sorry, I didn't hear you in like last minute.
Oh, sorry. Okay, yeah. I just got a message that I was having problems with my internet connection. So hopefully it doesn't. Hopefully it's better now. Yeah, make sure to tell me if you can't hear me. Although I guess if I lose connection, you can't tell me that I've lost connection, but I'll figure it out in that case. So right, so okay, so in this case, I take T equals C times C star. This is the fan. I have I take this as my divisor. This is the unique toric boundary divisor here. And then inside here, let me take Z to be just any, I can take it to be any point in this C star. So let's take point 0, 1 inside of 0 times C star. And then let's do this blow up. So once again, what I do is I blow up my, my toric variety at this Z, and then I'm going to delete the proper transform of the toric boundary, which this toric boundary is just 0 times C star. Take the proper transform and delete it. And my claim is that this thing that you get is actually equal to C2 minus XY equals 1. This thing that we started with. So there's various ways of seeing that. One way you could see it, kind of thinking about what it means to blow up this coordinate, and if you think about kind of the traditional definition of a blow up, so that's one way to see what's happening. So that's a good exercise that you can work out yourself is by sort of writing out this blow up explicitly in coordinates and checking that once you've deleted the boundary divisor, this is the coordinate ring you get. I'd like to sort of present this in a more symplectic way. Oh yeah, well, first of all, let me sort of present what I've done here in kind of a symplectic way. So, let me draw the moment polytope for T. So here's the moment polytope, right? It's just R times R greater than 0. This is Okay, I'm gonna erase this stuff here, but we know that I'm on for my toric variety in order to get a new moment vibration on this thing here. And so let's suppose that this is the point Z that I'm blowing up. So here's my point Z. What's going to happen here is I'm going to take a little triangle here, and I'm going to collapse it. Collapse this triangle vertically, so it just becomes a straight horizontal line. So then I get something that looks like this. It's going to turn out that this X is a singularity of the affine structure on the base. So what I'm going to get is now a new vibration where, so before, so this was a moment vibration for a toric variety. So before, the generic point of this vibration over a point in the interior, I had a smooth torus. And so that's still the case here. I have a smooth torus fiber. Whoops, that's supposed to be a torus. But over this point here, this line here, maybe I draw this thing in another color. Let me choose like dark green. So this is this color I'm drawing it in. Now this line is like this. This line here is the P1. This line here, whoops, I want black. This line here is the exceptional divisor of the blowup. So you can see it there that like all of these, uh-oh, my internet connection is unstable again. Oh well, I'm doing my best here. All of these horizontal lines here are, like if I take, let me draw in yellow, a horizontal line. This thing, right, is a copy of C. That's something I know how to read directly off this moment map picture of toric geometry. And now I can see that here, I have like a copy of C here, and it's meeting this P1 here. So after I delete, so okay, that was how I got a moment vibration on this blow up. And then of course, what I want to do afterwards is delete the boundary. So I've deleted this vertical line here, which was my toric boundary before. And once I've deleted that, my vibration looks like this. I have my 1x, and then everything else, I mean, I don't know, this is a vibration now happening in R2. So I have my one sort of singularity of this structure, and everything else is a smooth torus fiber. And now you can see that I have this vibration given by the like horizontal lines, where if I look at these horizontal lines, each of them is a copy of C star now. So this horizontal line is a copy of like C star, except for this horizontal line that's a copy of 2 copies of C meeting nodally. So this sort of matches up with the picture I drew at the very beginning of this talk of where I've got my vibration down to this B plane, where I have my, I've got the general fiber is the C star, and the special fiber is these 2 copies of C meeting nodally. Oh, and I even used the same color. That's so good. Yeah. So that's what this yellow thing is here. So the vibration down to like by this thing is like the vibration to the C plane, right? Unless I've gotten a coordinate backwards. Okay. So now that I've done that and explained, some of that Gross-Hacking-Keel construction, I'm ready to move on to symplectic geometry, unless there are any questions. Okay. So the symplectic construction, which I'd like to explain, is what's called a nodal trade. So I believe that this, oh yeah, and I should say, so these sort of pictures with the X's in them of vibrations that are almost like toric vibrations, but not really, those are called almost toric vibrations, and they're due originally to Margaret Symington, as is, I believe, the notion of a nodal trade, which was then picked up by Denis Roux and some of his students, and especially Renato Viana. So what is this nodal trade? So the idea of a nodal trade is start with the moment polytope for C2. So here's the moment polytope for C2. I'm just gonna erase this stuff, whatever. I can see that, maybe I'll write that. We can see, we can easily see in this picture the subvariety xy is equal to 0, right? That's these two lines here. That's the toric boundary. So that's something that it's very easy to see in this picture. But a motivating question is, what if we had instead wanted to see a smooth quadric? So instead of xy equals to 0, something like xy equals to 1. So that's my question. And the answer is, what you should do is modify the answer, introduce, uh-oh, my phone is ringing, excuse me, just a moment. Oh, it's a spam call, whatever. Introduce a branch cut in the integral affine structure on the base, so that this thing here, this boundary piece on the base, becomes a straight line in the integral affine structure, in the new integral affine structure, right? So the integral affine structure is precisely the structure which you get on the base of a Lagrangian Torus vibration in symplectic geometry. And what I'm saying is that, okay, you can see that right now in this picture, these two lines are clearly looks kind of singular because they're coming in like this. But what if I introduce a singularity in the integral affine structure, and I take a branch cut here? So this is a singularity, and this is a branch cut. Now, once I've done that, okay, let me go to a new page so things don't get too cluttered here. So once I've done that, this thing here is now smooth in the new integral affine structure. Right, the idea being that I've taken a singularity. I've taken a singularity here that has some kind of monodromy around here, and so I could have chosen, now that I've done this, I could choose a different branch cut, say, and in a different branch cut, maybe this would look sort of something more like this. Maybe the branch cut is going somewhere else now, like maybe it's going down like this or something, or that's not quite right. Anyway, my point was just to say that somehow this is something I'm allowed to do, and so it turns out that this thing now is the image of C2, the image of a quadrant xy is equal to 1 or something, rather than xy is equal to 0. So that's very cool. And this thing is the base of a vibration, and this diagram is the base of a toric vibration on C2. So this is a vibration on C2 now, where once again the Okay, I'm back. Hi, everyone. Let's share a whiteboard again. Oh no, so yeah, that's another feature request I have for the Zoom people. It like deletes your whole whiteboard every time you get disconnected. So that's a real bummer. Oh well, I can remember what I was drawing, which is I was drawing this vibration. I said that this was a toric vibration, almost toric vibration in the sense of Symington, almost toric vibration on C2. And I said that so the generic fiber was a torus, and it has one focus singularity, which is one of these nodal fibers. That's what symplectic geometers call this torus. It turns out that like in symplectic geometry, you know, introducing a singularity, this singularity in the integral affine structure that has the correct monodromy around it, that when you take a branch cut, you get this thing is smooth. That's exactly this focus singularity that gives you the singularity in the fiber. So, so the takeaway from this whole game is that I just wrote down some vibration on C2, which looks a lot like the moment map on C2, but not quite. And oh yeah, and in that vibration, this thing now is a smooth quadric, xy minus 1. So if I delete the boundary on the base, then now I'm no longer deleting the toric boundary of C2. I'm no longer deleting the toric boundary of C2. I'm now deleting this quadrant here. So what I get is a vibration on C2 minus xy equals 1. And once again, it's like a vibration that's got just this one singular fiber here. Okay, so that's very cool. What's next? So what's next is, so okay, now I'm going into my game. So in all of these, whenever I give a talk, I always end up talking about Lagrangian skeleton. That's like a big part of my life, is that like if you have a Weinstein, a Stein manifold, and you want to understand symplectic geometry, you'll understand the whole symplectic geometry in the sense of you'll be able to compute the Fukaya category of this thing. So I'm going to redraw my picture, and now I'm going to draw something new, which is I'm going to take a line coming out of this guy and going to a dot right here. So the fiber over this point here, as I've said, is a torus. And then what's the fiber over this thing here? It turns out, so the fiber is a torus. And the fiber over this thing here is a Lagrangian. So this is a Lagrangian torus, of course, Lagrangian, special Lagrangian, in fact, Lagrangian torus. And over this line here, I get a Lagrangian disk. Which is like it looks sort of like this. It's a disk that comes in and comes into this torus like that, and it hits this nodal fiber here. Right. So that's the point is that it's sort of, oh, I should have drawn it on the right side of this torus, but you can see what's happening. It's like in each of these torus fibers, it's this circle, which is getting smaller and smaller and smaller until it collapses to a point there in that nodal fiber. And so when I put these together, I get this total Lagrangian, which is this torus, which Lagrangian turns out to be, this is the Lagrangian, or A, Lagrangian skeleton, which I'm not going to review the theory of skeleton in this talk, but this is a Lagrangian skeleton for the variety C2 minus xy equals to 1. And so somehow, like once you know that, then that is going to allow you to compute Fukaya category of that thing. So maybe I'll talk about that in a second. First, let me sort of just explain what's happening in the original picture. So I can't go back, but I had this original picture where I had C2 minus xy equals to 1 is coming down to this, maybe it's coming down to this C star, which is what I was calling the B plane here. This is, B was equal to the coordinate xy minus 1. And it was missing a point here, and then it had one fiber here, which looked like this. And so what is this green torus I've drawn here? In the base, it's a circle around here. And then in each of the fibers, it's just a belt circle here in that fiber here. So this circle here is the circle where norm of x is equal to norm of y. And this circle in the base is the circle where the norm of xy minus 1 is equal to 1. So that's what this torus here is. This 1 doesn't have to be 1. In fact, it's not 1. I lied there. It can be any constant except 1. Or it could be 1, but then you would crush the disk to a point. So this is xy minus 1 equals constant. Oh yeah, and then what's the disk? The disk is projects down in this projection down to just this line right here. So the disk is actually the vanishing cycle for this Lagrangian here. So in other words, when I said Lagrangian skeleton here, you could have you didn't have to know symplectic geometry. You can just say, oh, we're doing like Picard-Lefschetz theory here. This is a perfectly good Picard-Lefschetz vibration on this variety, and it's got this critical point here, and that critical point has a vanishing cycle associated to it, which is this circle here. And so somehow putting together this torus over here with the vanishing cycle gives me this special Lagrangian that I like here. Okay, so that's the situation with this variety, which I know I've labored in a lot of detail, but it's my favorite example. So I spend like all day just thinking about this variety all the time. Right, so now how can we use this to compute the Fukaya category? Maybe I won't say this in detail, but I'll just give some hints about how this relates to the Fukaya category. And then I'll move on to some more general mirror symmetry statements. Category. If you have a Lagrangian L, so okay, if suppose you're interested, first of all, in the Fukaya category, all of my Fukaya categories will be wrapped. So in the wrapped Fukaya category of, let's as a warm-up, let's do C star squared. And inside here, this has a favorite Lagrangian of mine, which is the compact 2 torus. And so the answer in this case is that the wrapped Fukaya category of C star squared is equal to the category of local systems on this 2 torus. Maybe any Fukaya category of C star squared is equal to some category of local systems on this 2 torus. And so this category is, of course, modules over some category of modules over C adjoint xy, x inverse, y inverse. If I want the wrapped, I should really say perfect. Okay, I'm not caring about categorical details right now. This is just sort of a sketch of a calculation. And these x and y are recording the monodromies of your local system around the two loops in this torus. So X and Y are recording these monodromies. X and Y record monodromies of local system around loops. Okay, so that's what happens. That's what happens if you had a smooth Lagrangian torus. So in our case, we have our Lagrangian torus L, which was a union of a Lagrangian with a disk glued into it. And so what it turns out that we have here is, maybe I won't say that how to do the calculation right now, but since I'd prefer to talk about other things. But let me say that you're looking at some generalization now of local systems on this thing. They still have a monodromy here around this circle here. This is a perfectly good monodromy. Let me call it B. And it turns out that your sort of generalized local system on this thing has two maps here, which I'll call A and A prime. And the relation between them is the relation that A prime minus 1 is equal to B. So this exactly fits the description. In other words, the wrapped Fukaya category associated to the Lagrangian L is equal to modules over this ring A prime, B, A prime minus 1 is equal to B, and B is invertible, B plus or minus. So those of you who are familiar with the theory of perverse sheaves may, and some basic calculations there, may note that this looks a lot like a calculation you see in the theory of perverse sheaves, and that's because I just can't help pointing this out, that if you sort of crushed this disk to a point, which you could do without too much damage to your Lagrangian, then locally your Lagrangian looks like this. It looks like you've crushed it down to a point here, and then the rest of it is just a torus as usual. Then you can do this calculation as a calculation of perverse sheaves on C. And that's what sort of locally this calculation is. But I don't want to go into details about that. But that's a statement of mirror symmetry for this variety. So let me move on and now sort of summarize. Let's summarize what we've learned so far. A cluster variety, in the sense of Gross-Hacking-Keel, can be described by a fan of one-dimensional cones plus blow-ups plus blow-up data along some of the cones, along some of those which are rays. One-dimensional cones are also called rays. I'm asking for the fan to have only one-dimensional cones, and some blow-up data along some rays, which is precisely the choice of that you were blowing up something inside of that toric divisor, which will indicate which we can indicate by putting an X on the ray. I learned this trick from Andrew Hanlon. I mean, maybe he learned it from the original Gross-Hacking-Keel log Calabi-Yau surfaces paper. But what I mean, as an example, is in this case, T equals C times C star. When I did one toric blowup, I have a ray here. And let me give my X a color. Let me give it red. I just put a little X on this ray to indicate that I did a non-toric blow up there. Indicates a non-toric blow up. And so there's actually something very, very crucial going on here, which is that mirror symmetry switches Oh, wait, now I'm, okay, now this is the point where I always get confused in any discussion of mirror symmetry, what thing is happening where. And okay, in order to avoid confusing myself, I maybe won't say it, but I'll just say that it's in mirror symmetry, there's always two different bases that are happening. There's like an SYZ base of your space, and then there's like if you're a toric variety, you have your SYZ base, like the moment polytope of your toric variety. And then there's the Legendre dual of that SYZ base, which if you're a toric variety, that's where the fan lives. So this was where the fan lived for my toric variety, but now the X is living in the kind of Legendre dual space. And the X is telling me that, so the X reminds us that we have a singularity in the integral in the SYZ fibration of the resulting cluster variety. Yeah, so that's one thing now. So that was a summary of the Gross-Hacking-Keel thing. And then on the other side, in symplectic geometry, we can engineer an SYZ fibration with some X's in it, by starting with a toric moment polytope and doing nodal trades. So the example was we started with this guy, and then we did a nodal trade to introduce an X into him like this. But of course, this works in more generality. So the sort of moral of this talk now. So okay, I've only been talking about 2 dimensions. So my claim, the implicit claim of this whole talk is that a variant of my constructions that I'm doing here applies in any dimension. And this is sort of a way of producing mirror symmetry statements about. So my claim is that maybe I'll just I'll state the claim and then I'll go back to doing kind of examples. My claim is that for any GHK cluster data, we can produce a mirror whose Lagrangian skeleton is a torus with disks with subtori, maybe I'll write it this way, with subtori collapsed, with some subtori filled in, oops, with some subtori filled in. As before. So with some subtori filled in, I mean like over here, I filled in this subtorus here. I took this S1 and I filled it in with a disk. With some, we can prove homological mirror tree. So let me give a more, okay, I'm gonna go to the next page. Let me give a more general example so that people will believe me. I mean, not that much more general. I'm still just in 2 dimensions. And in fact, this example doesn't strictly fit into my, my story because one of the sides here won't be a cluster variety, but that's okay. So let T be the toric variety with the following fan. So, okay, let me draw myself a little grid of dots so I know where my fan is. It's hard to draw dots in this thing here. Right, so the fan I want is, yeah, the fan I want is this. So as it stands, of course, the toric variety associated to this fan is singular. So you can prepare that in two ways. You can either treat this as a fan for a toric stack. Okay, I'm back. Hi, everyone. Sorry about that. Okay. Sorry. So yeah, I do whatever. So as I was saying, you can either treat this as the fan for a toric stack, or you can add the 1, 2, 3, 4, 5, 6 extra arrays you need in order to get a smooth toric variety. This is a perfectly good fan. And then let me introduce some x's here. X, X, X. So what this is telling me is I take this toric variety or toric stack, and I do non-toric blowups along each of these three boundary divisors. Yeah, maybe let me just, in order for completeness sake, let me just make this into a smooth toric variety. So it's got a fan that's like this now, but I'm only introducing non-toric blowups on these three boundary divisors. And now what I'm going to do is in the mirror, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. I'm going to draw this polytope, which is a moment polytope for P2. And then what I'm going to do is I'm going to do nodal trades. I forget what color my nodal trade was. Was it also red? I'm going to use green, red. And then I do nodal trades on each of these three vertices. So you remember the nodal trade is like something that I do near a vertex to modify the integral affine structure at the base there. And I can do it on each of these three vertices because they all look the same after a transformation. I do like a do or whatever. And now I have my Lagrangian torus, which is here's my Lagrangian torus, and it's got 3 disks glued into it. And so it turns out that this cluster variety, the cluster variety obtained by starting with this toric variety and doing the described non-toric blowups is mirror to the result of this thing here. So I start with P2, and then when I do these 3 nodal trades, the boundary of this thing is now a smooth. So before I did the 3 nodal trades, my boundary was 3 nodal P1s. Each nodal trade smoothed one of the nodes. So now the boundary is a smooth elliptic curve. And so when I delete that boundary, I get P2 minus an elliptic curve. This P2 minus an elliptic curve is technically not a cluster variety. So normally cluster varieties are mirrored to each other. But in this case, it's not, because on the left-hand side, the divisor D I chose didn't support an ample boundary divisor, I think. Anyway, that's okay. That's 6 p.m. So that's the end of my talk. Thanks for coming, everyone. And yeah, questions or?
So is there some, what I mean is that, could you give me more detail why these two varieties are mirrored to each other?
Well, what kind of answer do you want? I mean, so there's 2 kinds of answer you might want. One is like mirror symmetry. Maybe it is something about geometry. And I've constructed for you SYZ fibrations on each of these varieties that are the same. right?
Yeah.
Each variety does have an SYZ fibration with exactly the same structure, except they're dual. Sorry, I've constructed dual SYZ vibrations on these two varieties. So you'd have to be more careful than I was about keeping track of things to see that, but you can at least see that, like, heuristically, they have the same SYZ base, right? They've got these three X's in there. The integral affine structure matches. So that's one answer. The other answer has to do with this calculation that I sort of hinted at before. So sort of, yes, oh, have I lost? Oh yeah, I disconnected, so I lost all my previous slides, unfortunately. But the calculation which I indicated before is that somehow, like, if I start with this torus here, which is the mirror to C star squared, and then I glue on this is a Lagrangian torus, and I glue on a Lagrangian disk. Somehow my claim is that that operation of gluing on that Lagrangian disk is mirror to this non-toric blow up and then delete the boundary divisor operation. That, like, if you compute the categories associated to each side there, then they're the same also. But that's kind of a more delicate computation than I had time to do in this talk.
I see.
But you can check, I mean, it's possible to compute that using this, oh yeah, so I should have said that this, you can see from this picture, sorry, maybe that was like a point I really should have emphasized here. You can see from this picture that the Lagrangian now I'm studying on the right-hand side is a torus with three disks glued in, and they're glued in along these three homology classes, the 1, 2, or sorry, 1, -2, 2, -1, and -1, -1. So, well, I can't draw them, but there's these three disks glued into there along those three. Oh, I can draw it like this. This is a T2, and it's got three disks glued in. One is glued in along here. One is glued in along like here. And one is glued in along like here, or something like that. Yeah, and that, I don't know, yeah, you study that thing.
I see, but then on the left-hand side, what should you compute in order to match this one?
Why should what?
So what I mean, you have three Lagrangian here, right, on the right-hand side, right? And
maybe, oh yeah, so okay, maybe, okay, let me give you a different answer, which I didn't emphasize in this talk, but if I have a, let me just do the one disk case. If I have a Lagrangian torus and it has a disk glued in, it turns out that I can collapse this disk and then grow it out the other way. So I collapse this disk to a kind of node point. And then I grow it back out the other way. And it turns out that now I have a smooth torus on both of these here. So I've got two Lagrangian tori. These are two different Lagrangian tori. And the point is that, like, local systems on the one Lagrangian torus and local systems on the other Lagrangian torus are related by a cluster transformation. That's maybe an answer that is more structural, the sort you might want. Local systems on these Lagrangian tori are related by cluster transformations. So the point is that if you start with a cluster chart, over here on the left-hand side, that corresponds to one of these tori. And now if you want to mutate and pass to a different cluster chart, then I'm telling you how to do that. It's like you crush one of these disks and grow it back out again. So I've given you kind of a way of passing between all the different cluster charts of your variety. And the fact that so I didn't have time to say this either, the fact that there's cluster varieties have something to do with, have some canonical bases inside their coordinate rings, has something to do with that inside this two torus, if I draw, well, right, if I draw my two, if I draw my two torus like this, and then I say, like, here's the disk I was gluing in, I told you there were kind of these two variables, A and A prime, that were allowed to kind of go between them, but one of them is more natural than the other. So kind of by studying kind of paths on your certain homotopy classes of loops on this torus, those provide the canonical basis of the mirror. And you can see them in different cluster charts, and the mutation rules match up and everything.
Okay, thank you. Okay.
Any other questions or nope?
So I have a question.
Oh, yeah.
Yeah, starting from point of an toric variety, we can consider the Caravia variety as a hypersurface section, but not only the hypersurface section, starting from the Minkowski sum, we also obtain the Caravia as a toric complete intersections. So in a similar way, could we consider a kind of cluster variety starting from the data of the Minkowski sum of Poitovs or something like that?
Oh,
according to my memory, even such a case, we have a mirror symmetry.
That's an interesting question. I don't know off the top of my head. I haven't, I have never thought about, I've only really thought about hypersurfaces in the past. So I would have to think a little before I have something to say to you there. But that's definitely an interesting question. Yeah. I don't know.
Thank you.
So I'm sorry for keep asking, but may I ask you one more time that, so you told me what is the canonical basis corresponding to the, did you say that maybe?
Well, I didn't really explain it. Maybe, yeah, I'm happy to answer more questions. Let me just say, okay, people are free to leave at this point if I don't want to keep people if I'm just answering questions, but let me move to a new slide. The idea is like, let me draw my torus like this. So I told you I had a torus with a disk glued in, but really it came in some way, it was sort of like this. I have a torus with a cylinder here, and then it capped off with a disk over at the end, like this. And so before I cap off this disk here, so before I cap off this disk here, I can draw this thing like this. This is just a two torus, and then it's got a certain subtorus inside of it. Maybe I should draw this thing in a different color, like this thing is red. It's got a certain subtorus inside of it, and then this thing at infinity, maybe it's this thing at infinity, I don't know. This is a Lagrangian inside of the cosphere bundle of the two torus that I started with, and this thing is the cone on that Lagrangian. It's the cone on that Lagrangian, so it lives inside of T star T2. This is a conic Lagrangian. Conic Lagrangian. And a conic Lagrangian, a Lagrangian at infinity can be specified by specifying like a real hypersurface in this torus with a co-orientation. So I co-orient it by drawing these hairs here. And then if I wanted to compute the sort of Fukaya category associated to this object, now the rule would be very simple. The rule is I'm studying kind of local systems, except I'm allowed to have non-invertible monodromy as I cross the hairs in this one direction, down like this. So my two torus now, in other words, has a usual monodromy going like this. This I'll call M, or I'll call B maybe. And then it has this non-invertible monodromy A. So the sort of Fukaya category associated to this object, associated to this, is modules over, so I've got my two monodromies, only B is an actual monodromy and A is allowed to be non-invertible. So in other words, it's a mirror to functions on C times C star. So that was like functions on this sort of toric variety that we started with. The point is that if you were to crush this, if I were to cap off this disk now, anyway, this is the part of the canonical basis associated to this cluster that we started with. If I had moved to the other cluster, so there's another cluster where sort of I cap off this disk and I crush it and it glues back out the other way, and now he's sort of co-oriented the other way. I've also done a Dane twist to my torus in the meantime when I did that procedure. Oops, sorry, that was the same as before. No. Then I get I get B again, which is this monodromy here, B, which is invertible. And then I get this thing here, which is going here, and this is A prime. So I get C joint A prime, B plus or minus. And so the canonical basis of functions on this cluster variety is like the union of things that are a monomial in A and, I mean, a positive power of A and a power of B, and things that are monomial in a positive power of A prime and a power of B. And that has to do with that you're sort of respecting that your sort of path in the torus was respecting the co-orientation of this circle that I drew on there. Sorry, I know that's like a lot and it's kind of hard to explain, but.
Thank you.
Yeah.
Thank you very much.
Cool. Any other questions? All right, if not, then thanks for coming, everybody. I guess that's it. So I'll.
Yeah, thank you.
Sure.
Thank you for the presentation.
Yeah, thank you very much. See you.